This lesson is going to be over the applications of the ideal gas law. There are some ways that we can derive or the equation for the ideal gas law and solve for other things. And so that's what this lesson is going to be about. Some teachers will make you just derive this gas law, but there is actually a simple formula that I'm just going to give you that you can use to solve for molar mass or density of a gas. Okay? So if you want to solve for molar mass, and we're going to do molar mass as mm, molar mass, we're going to do that as dirt, dRT, over pressure. Okay? Dirt over P is what we call it. Okay? And so that D is going to be density. Okay? So D is density, and recall that density is mass over volume. Okay? All right? And then molar mass, of course, is grams per mole. All right? And then if we want to solve for density, we can actually use the molar mass of a gas times pressure over RT, which remember R is the gas law constant. And so if it's asking you for something like molar mass or density, if you will use these two equations instead of trying to derive the other ones, it just makes it a lot easier. Okay? So let's do a couple of examples, and then so this first two examples are going to be about determining molar mass. So this says determine the molar mass of a gas that has a density of 2.75 grams per liter at 729 torr and 60 degrees Celsius. So first two things I see that I need to do is I need to do temperature of Kelvin. So I'm going to immediately do that. And 60 plus 273 is 333 Kelvin. It gave me pressure in torr, and that's not going to work for the gas laws because I have to be in atmosphere. Because remember, my units of R, 0.0821, is liters times atmosphere, mole times K. Okay, so my units have to be in atmosphere to match that. So I'm going to need to change my pressure to 729 torr. And I'm going to need to use that conversion factor. 760 torr is 1 atmosphere. And I'm going to put that into 3 sig figs because that's what I started out. So it's going to be 0.959 atmosphere. So now that I have my two things converted, I can use this formula that I just gave you. Molar mass is equal to dRT over P. Density is D. So this is density. So we're going to plug that in, and we're going to say 2.75 grams per liter times my R value, 0.0821 liters times atmosphere, mole over K. My temperature of 333 K divided by pressure, which we had converted to be 0.959 atmosphere. So what's going to cancel out is Kelvin, Kelvin, atmosphere, atmosphere, liters and liters, so that I'm left with grams on top, moles on bottom, which is what my units of molar mass are, grams per mole. So now when I multiply the top and divide by the bottom, I would get 78.40, keeping in mind we always do molar masses in 2 decimal places. Okay? And so let's work another one just to make sure you get this, how to do it. And I wanted this one that we work is not going to outright give us density, but it's going to give us what we can use to calculate density, because we're still determining molar mass, so we still need this mm equals dRT over P. Okay, but when we go see density, it doesn't give it to us, but it does give us a volume, and it gives us a mass. And remember, density is equal to m over v, mass over volume. So we're going to calculate our density real quick. Okay, m over v. So our mass was 12.8 grams, but our volume is in milliliters. And in gases, we're going to need this to be in liters. So we need to do a quick conversion real quick and say 754 milliliters. We need to convert that back to liters. So there's 1,000 milliliters in 1 liter. So it's 0.754 liters. So 0.754 liters on the bottom. So we do that, and we get a density of 16.98, but if we use correct significant figures, it's going to be 17 grams per liter. So now I can plug it into my problem, okay? Except I go back up here and look, kilopascals for my pressure, okay? So I'm going to need to do a quick 1.205 kilopascals. The conversion for that from day one was 101.3 kilopascals per 1 atmosphere. And then that comes out to be 1.01 atmosphere. Of course, my temperature, we should have done that. We usually do that right away, and I forgot to. That's going to be 358 Kelvin. So now we're ready to plug everything in. So my density, we said, was 17.0 grams per liter. My rate is 0.0821 liters times atmosphere, moles times K. I'm going to draw this little line here because I'm running out of space, times 358 Kelvin, divided by my pressure of 1.01 atmosphere. When I do all my canceling, I'm left with grams per mole. And when I put that one into 2 decimal places, I get 494.71 grams per mole. Now let's practice to solve for density. Okay, so this time it says what is the density? So we're going to use density is equal to molar mass times P over RT. And this one wants to know what is the density of gas that has 3.00 moles in this atmosphere and Kelvin temperature if the sample has 15.9 grams. So we don't need to do any converting as far as atmosphere or Kelvin because it's in the units that we need, but we're going to need a molar mass. And it didn't tell us what gas or what sample. Yeah, it's a gas. Obviously, we're doing the gas levels, duh. So it didn't tell us what our molar mass of the gas is, but it did give us enough information that we could figure that out. Because remember, molar mass is equal to grams per mole. And they gave us grams, 15.9 grams, and they gave us moles of 3.0 moles. So we can figure out molar mass based on the fact that they gave us grams over moles. And so when we do 15.9 divided by 3, we get 5.30 grams per mole. So now we have a molar mass that we can plug in. So let's go find out what our density is. So 5.30 grams per mole times our pressure, which was 2.31 atmosphere, divided by, that looks like RT, 0.0821 liters times atmosphere, mole times K. And then our temperature was 311 K. When we start canceling out, we're going to be canceling out moles, we're going to be canceling out atmosphere, and we're going to be canceling out Kelvin, which is going to leave us with units of grams over liters, which is what our density unit is in. And so when we multiply the top and divide by the bottom, we're going to get we're going to get 0.479 grams per liter. And that is our density. Okay? I think we have one more problem to work on this. Okay? And that is another density problem. And this wants to know what is the density of oxygen. So since we know the gas, we can find the molar mass. And remember, oxygen gas is O2. Okay, so that means we're going to use a molar mass of 32 grams per mole. Because remember, when oxygen gas is by itself, it's diatomic. It's one of the Brinkelhoff, so it's 32 grams per mole. Okay, we're in the right atmosphere. Temperature, we got to quickly convert. Excuse me. And so 308K is what that's going to be. So now density equal to molar mass times pressure over RT. So we can just plug all that in real quick. So we got 32 grams per mole times our pressure, which was 1.23 atmosphere, divided by our R value, times 308K on the bottom. Cancel, 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 cancel. Whoops, just kidding, that one stays. It's moles I meant to cancel. So our units are grams per liter again. And I do the math, and it looks like everything needs 3 significant figures. My answer is going to be 1.56 grams per liter. And that brings us to the very last part of the lesson, and that is not gas stoichiometry for you guys, so you guys can skip this. And you can skip this. So we're just going to skip, skip, skip. And that brings us to effusion and diffusion. Okay? And effusion and diffusion, and this is kind of showing them, is the movement of the gas particles. Okay? So in diffusion, okay, you're going to have the gradual mixing of two gases due to their spontaneous nature. Okay? And basically, that is why we can smell things like perfume, or when we burn toast, or, oh my gosh, burnt popcorn is the worst. But when someone makes popcorn, and all of a sudden you smell it and you want it, and that's due to diffusion, because their spontaneous motion, it spreads throughout the room. Okay? Effusion is a little bit different. So diffusion happens quickly in gases because the gas particles move so rapidly. Okay? And so they're moving around all the time, so they will mix together. Okay? In effusion, okay, the process is a little different. There we have molecules escaping throughout a tiny opening in the container. Okay? So random motion means eventually those particles are going to come out. Okay? Different with pressure involved, because pressure will equalize. But if it's just an opening, and that's what's going to happen, it's just going to eventually come out. So a very good example of that is a helium balloon. Okay? So if I have a helium balloon, it doesn't sit there and stay forever, because eventually what happens is the helium effuses out of the balloon faster than just the air, because the helium moves faster. And so that's why we get flat balloons. Okay? And so here's just another example. The rates of diffusion and effusion depend on the velocity of the particles and the mass of the particles. And so for our purposes, that's all we really need to know. We are going to skip that last section on the Graham's law, so you can mark that out, and that is the end of the gas law notes for us.